Good afternoon. Welcome back to week 7 problem solving session. So I am Shreya, one of the TAs for this course, and today we'll be discussing few of the problems based on the concepts discussed so far. So before getting started, can you see my screen and hear me? If you could please confirm. Okay. So let's get started then. Fine. So in this week, we learned a lot about variance covariance matrix, how the multivariate normal distribution looks like, some probability and moment generating functions, and we learned about cross moments, which were the covariance, and also about correlation coefficient and conditional expectation. So based on these and few of the concepts that was discussed beforehand, we'll solve a few problems. So without any further delay, let us jump on to the first problem for today. So can you see my screen? Can you read it? It's visible, right? All right. So the first problem is emails arrives one at a time in an inbox. Let Tn be the time at which the nth email arrives. Suppose that the waiting times between emails are IID exponential lambda. Then if each mail is spam with probability Q and non-spam with probability P, then if X is the time at which the first non-spam email arrives, then find the mean of X. So, how should we solve this problem? So, let X equal to x1 plus x2 plus xn be the time at which the first non-spam mail arrives. Okay, so where xj denotes the duration between j minus 1th email and jth email. Okay, so xj is equal to tj minus t of j minus 1, and we have been given it follows IID exponential lambda. Okay, now let us consider B the trial, or let n be the total number of mails received before total number of mails received to till the first non-spam email. Okay, so which essentially means that the nth email is the non-spam email. Is it clear, this part, the formulation? Okay, so this is already given to us. Now okay, so this part, I hope this is clear. Okay, yes, all right. So we can say from here, if n is the total number of mails received till the first non-spam mail. So non-spam mail is my, so here when we are considering in terms of n, then non-spam mail is my success. Let's say this is what we want. All right, and spam is the, let's say, failure. We don't want. So success probability is P and failure probability is Q. Now n is similar to what? Number of trials till first success. Okay, so this will follow a geometric distribution, geometric P. Okay, so in our terms, it is number of emails received till first non-spam. So this also follows geometric P. This part is clear. Now n is the total number of trials. So expectation of n will be 1 by P, and expectation of, and variance of n will be Q by P square. And PDF probability n equal to small n will be how much? Will be Q to the power n minus 1 into P. This is okay? Alright, where n can be from 1 to ... to anything. Alright, so this is the formulation of n. Now we have to find out the probability, the time, expected time at which the first non-spam email arrives. So here we have written x equal to, x equal to x1 plus x2 plus x3 plus xn, where this is the arrival of first mail, arrival time. This is wait time to second email, and so on and so forth. Okay, so this one, x1 equal to t1, x2 equal to t2 minus t1, xn equal to tn minus 1, where tn is the waiting time, let's say. So it has been given that what has been given? Given is x1, x2, xn given n follows exponential lambda. Therefore, expectation of x can be written as expectation of x given n. So once n is fixed, which trial is receiving the non-spam email, we are not bothered about that. Then these are only wait times, and the wait time is identically distributed with exponential lambda. Therefore, the expectation of x given n can be written as expectation of summation xi I equal to 1 to n given n. Okay, so this we can write as expectation so this we can write as expectation of x1 given n plus expectation of x2 given n plus expectation of xn given n. So each of the xi given n follows exponential lambda. So expectation of these will be 1 by lambda. So here we will write expectation of 1 by lambda plus 1 by lambda plus 1 by lambda. This will be n times. Okay, so this will be then expectation of n by lambda, and then we can take 1 by lambda out. Expectation of n is, here we have written expectation of n is 1 by p. So the answer is 1 by p lambda. Okay, so what we are doing essentially, expectation of x, we are writing it as expectation of x given n. So this expectation is over x and this expectation is over n. Okay, so once n is fixed, we know that xi's are the waiting times and which are identically distributed with exponential lambda. So we'll just write it as summation xi given n, and then this is the same thing as individual given n. Those follow exponential lambda. It will be 1 by lambda because the fx given n is e to the power lambda e to the power minus lambda x when x greater than equal to 0 and 0 otherwise. This is the PMF. Okay, so then the expectation value will be 1 by lambda. 1 by lambda we'll write it over here. So this inner one is with respect to x, outer one is with respect to n. And then once we have n by lambda, we are going to put the expected because we know n follows geometric p. So expectation of n by lambda will be 1 by p lambda. Is it clear? Any doubt? Okay. So we'll move on to the next question. So I think Dr. Lenina has joined recently.
Yes, yes, Shreya.
Yes.
Good afternoon.
Good
Yeah,
afternoon, ma'am. So I just finished solving the first problem. Do you want me to repeat it for you?
please.
Okay.
Actually, I was in a program, so I couldn't
Okay, I
join on
understand.
time.
I understand. Fine. So this was my problem. Emails. This is the question. Emails arrives one at a time in an inbox. Let Tn be the time at which the nth email arrives. Suppose that the waiting times between emails are IID exponential lambda, and each email is spam with probability q and non-spam with probability p, where p plus q is 1. Let x be the time at which the first non-spam email arrives. So you have to find the mean of x. Now we can write x, that is the time at which the first non-spam email arrives, as let us assume that the non-spam email arrives after capital N minus 1 spam emails. So we can write x as x1 plus x2 plus xn, given that xn is the waiting time between the last spam and non-spam email, and x1 is the time to get the first spam email, x2 is the waiting time between the first spam and the second spam. So each xj, let it denote the time duration between the j minus 1th email and the jth email. So this is essentially tj, whatever tn has been mentioned, minus tj minus 1. So this waiting time or the duration between emails, it is following IID exponential lambda. Alright. So and now n, if we consider that the nth email is the first non-spam email, n essentially means that the total number of mails received until the first non-spam email. So the distribution of n is geometric p, where p is the probability of getting a non-spam email and q is the probability of getting a spam email, and our n is number of emails received till the first non-spam. So number of trials till first success. So this will have a,
How did you decide that it would be a geometric distribution?
because it is similar to this one. Geometric distribution is determined by number of trials till first success, or number of failures before first success.
Okay.
This is the form of a geometric distribution, no? So this form, it means that we have n minus 1. So n, when it starts from 1, it means that we are getting success at first trial, success at second trial, first success. This is how the geometric is framed. In case of binomial, what do? Binomial, we have total number of successes in n trials. That is by definition a binomial distribution. Similarly, by definition, geometric is number of trials till first success or number of failures before first success.
Okay.
Okay. So this n, it is following a geometric p. For this form of geometric distribution, expectation of n is 1 by p and variance is q by p square. This we already know. So now expectation of x we have to find out. So x we are writing in terms of, we are breaking it down into waiting times. Each of these we know are independently IID exponential lambda. So expectation of x, we can write it as expectation x given n. Okay, so this expectation will be with respect to x because we are fixing n, and the outer expectation will be with respect to n. Okay,
Okay.
now x we'll write as summation xi given n. This we can write, if we expand, we can write it as expectation of x1 given n, x2 given n, and xn given n. These are IID random variables because these represent the waiting times between two successive meals. So this will follow exponential lambda with this form of the PDF usually, and then the mean value will be 1 by lambda. So we'll substitute the expectation values over here. This will be added n times, so we would ultimately have expectation of n by lambda, and since n follows geometric p, we would have 1 by lambda into 1 by p. So 1 by p lambda is my final thing.
Okay.
Okay, so we'll move on to the next one. This is also a similar thingy, exactly same problem, but we have to find out the variance. So it says that one bus at a time arrives at a bus stop. Let Tn be the arrival time of the nth bus. Assume that the wait duration between buses are exponential mean. There is no passenger in each bus with probability P, and there is at least one passenger with probability Q. Let x represent the arrival time of the first bus with no passengers. So similarly, we'll write x as x1 plus x2 plus xn, where n is the first bus with no passengers. Okay, and here xj is waiting time between arrival of j minus 1th bus and jth bus. x1 equal to t1, x2 equal to t2 minus t1, tj minus tj minus 1. This is my formulation. So here also n follows geometric, no passengers is my criteria. This is what we want. So this is my success probability. So geometric p. Okay, if we would have wanted a bus with at least one passenger, it would have been geometric q. That is what we want. That is my success. So first bus with no passengers, n will follow geometric p. So now we have to find out variance of x. This thing we have to write as expectation of variance of x given n plus variance of expectation of x given n. This thing we should keep in mind. For expectation, this holds. Expectation of x can be written as expectation x given n. But for variance, we cannot simply write variance of expectation of x given n. Variance of x, when we do conditionally, then this is the formula that we should use. Alright, now we'll move on to get the values of each one. So expectation of variance of x given n. I'll rewrite it again here. Variance of x equal to expectation of variance of x given n plus variance of expectation of x given n. So this we can write as expectation of variance of summation xi given n plus variance of expectation of summation xi given n. Okay, so this will be expectation of, now since xi's are IID, it has been given, we'll assume, okay, wait time durations are IID, nothing is mentioned, that will make our case easier. So then we can write it as, since these are independent and identically distributed, we can write it as summation of variance of xi given n. We cannot write it always if they are not independent, because then we would have covariance terms. Okay, plus variance of expectation of summation, or we can write it as summation expectation of xi given n. So these we have found out this thing. This will be what? This was n by lambda. Each of these were 1 by lambda, so we summed it up till n, I equal to 1 to n. Okay, now variance of xi given n, variance of xi would be, so xi given n follows exponential mu, it has been given here, exponential mu. So expectation of xi given n will be 1 by mu, and variance of xi given n will be 1 by mu square. So this one will have expectation of summation I equal to 1 by n, 1 by mu square. So this will be expectation of n by mu square plus variance of n by lambda. Now n follows geometric p. Expectation of n would be 1 by n, variance of n would be q by p square. So here we would write it as expectation of n is 1 by p mu square plus variance of this is 1 by lambda square variance of n. You remember, no, variance of ax is a square variance of x. If we have multiplied any random vector with a scalar, random quantity with a scalar or a fixed value, then this will come out as a square. So here we have, I'll write it separately, we have 1 by p mu square plus 1 by lambda square variance of n. So this can be written as 1 by p mu square plus 1 by lambda square p square by q by p square. So we can write it as, okay, this will not be lambda, this will be mu. I am making a, here we are writing everything in terms of mu. So this also will be mu. My bad. So this will be mu. This will be mu 1 by mu square. So here also we have one by mu square p square 1 minus p. So this we'll write as mu square p square p plus 1 minus p. So this would be 1 by mu square p square. Is it okay? Any doubt? So if there's no doubt, I'll move on to the next one. I hope this is okay. All right. Is the screen visible and am I audible?
Ma'am, you are audible.
Okay. But the screen is not visible.
Pardon?
The screen is not visible.
It is.
Okay, fine. So
Yeah.
I thought there was some drop in connection.
No.
Okay, fine. So we'll move on to the next one. So this is the question. One of two identical looking coins is picked from a hat randomly, where one coin has probability P1 of heads and the other has probability P2 of heads. Let X be the number of heads after flipping the chosen coin n times. So now we have to find the mean and variance of X. So let us write I. Let us define an indicator which take value 1 if coin with P1 heads probability is chosen and 0 if coin with P2 as heads probability is chosen. Okay, let x1 denote number of heads after, let us denote this as coin 1 and let us denote this as coin 2. Okay, x1 denote number of heads after tossing coin 1 n times. Okay, and x2 denote number of heads after tossing coin 2 n times. So x can be written as I x1 plus 1 minus I x2. Is this clear so far? See, when I is 1, x will be x1, and when I is 0, x will be x2. All right?
I mean, how we are framing this expression?
See,
What is our requirement basically?
our requirement is to we have to we have two coins.
Hmm.
Now we have to induce randomness in choosing one of the two coins.
Hmm.
We can choose either this one, either this one. If we frame it in this manner using this indicator variable,
Hmm.
this is also a random variable.
Okay.
Okay, I is also a random variable where each of the coins is picked randomly from a hat. So getting probability of I equal to 1, probability will be half. I equal to 0 is also probability half. Okay, so this x thing depending on which coin I am choosing, that coin has to be flipped n number of times. So it can be
Okay.
the first coin, it can be a second coin. That is chosen randomly. So in order to incorporate these two events together, we can write it in this manner. So when I is 1, this is 0, so x is x1, that is number of heads obtained after tossing the first
Tossing
coin.
first coin.
Yes, and when I is 0, that means the second coin is chosen, then we'll have only x2 and x1 will go away.
Okay.
Okay, so mathematically this randomness can be incorporated in this framework using this indicator variable.
Okay.
Now,
But is there any, I mean, book or any reference by which we can have this kind of framing?
book or reference, any standard probability and inference textbooks will have these kind of things.
Okay.
Okay, so you can pick up any, you can suggest, I would suggest you go through Mood Grable Bose and Ross's probability book. Those will
Okay.
have
Ross and Mood.
Mood Grable Bose. So I'll write it here, references in a slide and share with you. Mood Grable Bose. They have a book on inference. Here you will get, I think, probability, Sheldon Ross's Introduction to Probability, or any other standard textbook. Okay,
Okay.
here you'll find it. All right. So this is clear to you how we can frame. Now this becomes easier. So here now we have to find the mean and variance of x. So expectation of x we can write as expectation of I x1 plus 1 minus I x2. Okay, so this one we can write as expectation of x given I. So now we are fixing which I am choosing.
Okay.
Okay, so then this will be expectation of I into expectation of x1 plus 1 minus I into expectation of x2. So this one we can write as expectation of I. Expectation of x1 is x1 follows binomial in P1. x2 follows binomial np2. So this will be I into np1 plus 1 minus I into np2.
Okay.
Okay. So then here again this will be with respect to I, then we would have np1 expectation of I plus np2 expectation of 1 minus I. Okay, or we can write it as np2 1 minus expectation of I. Okay,
Okay.
now I is taking 1 with probability half and 0 with probability half. So
Okay.
expectation of I is 1 into
Half.
half plus 0 into half, that is half.
Half.
So then here we would have, this would be
0.5
np1
NP1.
half plus np2 1 minus half. So it will be half np1 plus p2. Is it okay?
Yeah.
All right. So then variance of x. Variance of ix1 plus 1 minus I x2. This we can write as variance of x given I expectation plus variance of expectation of x given I. Okay, so
Okay.
this one we can write as, now separately I'll do it and pitch it over here. So variance of x given I is what? Variance of ix1 plus 1 minus I x2 given I. Now I is fixed, so this one we can write it as I square variance of x1 plus 1 minus I whole square variance of x2.
How did you write this?
I is fixed given I, so I square will come out, variance of ax equal to a square x.
Okay.
Okay, now see I is an indicator variable 1 0 with probability half half. So I square will also be I, because it will be 1 square is also 1 with half, 0 square is also half with probability half.
Okay.
So I and I square can be written interchangeably. Okay, so this one we can write as I into variance of x1 plus, even 1 minus I is the reverse thing. 1 minus I is also where, when I is 0, 1 minus I is 1 with probability half. Probabilities are also not changing. So
Okay.
this one also we can write as 1 minus I into variance of x2.
Okay.
Okay, now x1, as I said, x1 follows binomial np1, x2 follows binomial np2. So this will be I into np1 1 minus p1 plus 1 minus I np2 1 minus p2.
Okay.
Okay, so this one we got an expectation of x given I is what? Expectation of ix1 plus 1 minus I x2 given I. This will be what? I into expectation of x1 plus 1 minus I into expectation of x2. So it will be what? I into np1 plus 1 minus I into np2.
1, 2.
Okay, so we'll just substitute these values and we'll see what we get. So therefore variance of x would be expectation of variance of x given I plus variance of expectation x given I. So this one would be expectation of variance of x given I is this part I n p1 1 minus p1 plus 1 minus I n p2 1 minus p2 plus variance of I into np1 1 minus I into np2. Okay,
Okay.
this one we have. Then variance of expectation of I is half. So this will be half np1 1 minus p1 plus again half np2 1 minus p2. Alright,
Okay.
plus variance of I np1, it will be what? N associated things will take out. So this will be n square p1 square. Variance of I will be one by 4 plus 1 minus I square will also be
1 by.
1 by 4 n square p2 square, and then after solving whatever comes, that is the answer. Okay,
Okay.
all right. Fine.
Actually, Shreya, I am teaching this subject to second year students.
Okay.
So, I mean, how to make this subject interesting? Because so many formulas needs to be memorized, and so many references needs to be taken. This equation to be put here, this equation to be put here. So it makes the subject very dry. So how to make it interesting?
Ah. This is something like even I struggled with, because there are a lot of formulas, but once the why behind these are clear, it's easier to remember that way.
Yeah.
So if you could show them or give them some proofs of these results, how these are coming, then I think you don't need to memorize that much.
Okay.
Second year students, I think they would just get started on these probability concepts and expectation
Yeah.
variance and these. Hmm. I think uh, knowing the whys helped me, so I think that will help the students remember, and the
Okay.
concepts that why of independence and dependence, where the covariance terms happen, and the rest of it is just mathematics.
Yeah, and that for engineering students, that
Hmm.
needs to be correlated with the engineering subject and taught. So they'll get something new out of it. They find application. Otherwise, they start studying mathematical point of view only.
Okay, okay, all right. So these problems will might be helpful in their context. Like here, if you are, I don't know which stream you are teaching, but
Electronics,
electronics.
electronics and telecommunication. Yeah.
Okay, so I have no idea of that field, but if these problems can be, tailored to the interests of the students and the applications that happen from an electronics perspective. Like if you are teaching, we'll do, I think, in later stages some testing of hypothesis and those kind of things. So usually we would test for two means or something like that, but in an electrical concept or analogously, we could find means, the mean difference between the signals that
Hmm.
that arises. So if these problems with the same parameters, if it could be tweaked a little, according to the applications that are present for, I mean, that are there in electronics, I think then the students would find it interesting and
Okay.
applicable, because these are essentially some processes, arrival times, and so those kind of processes also happen in productions and um,
Yeah.
these kind of scenarios. So if I can understand like this process, if we can tweak, you know, that's what I don't know anything about electronics, so nothing is coming to my mind right now.
Okay.
uh,
Okay.
so
Yeah.
if you could do that, that will be helpful for the students.
Okay. Thank you.
Okay, thank you. So we'll move on to the next one. All right. So here they are saying that two fair six-sided dice are rolled. One is green and one is red, with outcomes x and y respectively for the green and red. So let us. So what outcome is there that is not specified over here? Okay, but what is specified is that there is one green and one red. So
Hmm.
outcome in the green one and the red one is supposed to be independent of each other. We have two die, whatever comes here, whatever comes here, we would assume it to be independent, but still for the sake of doing it, we'll do it. So and x and y, let this be outcome from the red one. Okay, and then let y be the same outcome from the green one. Okay, so apart from color, these are identical. Okay, this will also have 1 2 3 4 5 6 outcomes with probability.
1/6 inch.
So 1 by 6, 1 by 6 each. Here also x and p would be 1 2 3 4 5 6 with 1 by 6 each.
Yeah.
So x and y are identically distributed. Okay, so then here covariance of x plus y and x minus y we can write as covariance of x plus y, x minus y. This can be, can split it up. This can be x plus covariance of yx minus covariance of xy minus covariance of yy. Okay, so covariance of x and x is essentially variance of x. Covariance of yx and covariance of xy is the same thing, so these two will cancel, and covariance of yy will be variance of y. Okay, now
Okay.
variance of x, since these are identically distributed, whatever will be the variance of x, the same thing will be the variance of y itself. So
Yes.
then this will come out as 0,
0.
since x and y are
Identical
identically
distributed.
distributed. Okay, but if one was 1 by 6 and one was biased, then so easily we couldn't have done it. We would have to calculate the
All.
variances for each and then get the whatever it was, whatever value comes. Okay,
Yeah.
all right. So we'll move on to the next one now. All right. So if x is a continuous random variable such that expectation of x to the power r exists, then expectation of xn will exist for all n less than r.
How?
This happens, how I don't remember the proof right now, but this is like a result.
Okay.
So the higher order moments should exist for the lower order moments to exist.
Okay. If higher order movement exists, then
Hmm.
lower order movements
Should
should
exist.
definitely
Yes.
exist. Okay.
Provided this exists means expectation of mod x to the power r is less than infinity.
Okay.
Okay. So moment exist, uh, we saw in some things that sometimes the absolute, if the absolute value doesn't converge, then moment doesn't exist. Then there's no question of this exists means that this absolute value to the power r will also converge.
Okay.
Okay, all right, this one. So let us consider a continuous random variable with PDF given by this. Then which of the following options is or are correct?
XFX. First one correct.
Okay.
Expectation of mod x is 1.
Hmm.
I think A is correct.
Hmm.
And next is variance of x. X square raised to x and C.
Yes. So I'll just write down how we are doing it. Expectation of mod x is integration of mod x fx dx. So this will be from minus infinity to 0, mod x is minus x and fx is e to the power x by 2. And from 0 to infinity, mod x is x
E raised to
and
minus
this
x.
is e to the power minus x by 2. So this will come half, this will also come as half. Finally, we would add up at 1.
1.
And this would can be solved by this by parts, integration by parts.
Okay.
Okay. All right. So,
For variance, we take square.
so for variance, we'll take square. Yes. So variance of mod x will be
Expectation of x.
expectation of mod x square minus expectation of mod x whole square. So this will be the same as expectation of x square minus expectation of mod x whole square. This one will be 1.
Yeah.
So this will be from minus infinity to 0, x square e to the power x by 2 dx plus 0 to infinity x square e to the
E
power
raised to
minus x by 2 dx minus 1. This will come 1, this will also come 1, 1 minus 1, so 2 minus 1, we will ultimately have 1.
Yeah.
Okay, another shortcut thing that you can see over here. So this thing is nothing but half into mean of an exponential distribution with lambda equal to 1.
Okay, x lambda, e raised to minus
Hmm.
x lambda. So
Hmm.
lambda is 1.
Lambda is 1.
Okay.
So this is expectation of
X.
exponential with mean 1. So
Yeah.
that mean will also be 1. So this is half. And here also if we replace uh, x by minus x, then we'll for let's suppose here let y equal to minus x. So dy will be minus dx here we'll have something. So this will also then become 0 to y to the power minus y by 2. That is also a mean of a y distribution, mean of a random variable y which follows exponential 1. So that will also be 1. So here we'll have half, here we'll have half plus half equal to 1.
Okay.
This is like a quick thing to do instead of going, you know, doing integration by parts all over again. Alright, so we'll move on to the next one. So now let us suppose that we have two variables x and y which have the joint PMF like this. So x and y are discrete random variables.
कशी सही केली होती परीक्षेची?
Okay.
Yeah.
Okay. So x can take these values, y can take these values. These are the joint probability distribution. Everything is adding up to 1. These are the marginals for x and marginals for y. Then what is the correlation coefficient of x and y? So correlation coefficient xy, which is written as rho xy, this is nothing but covariance between x and y by square root of variance of x into variance of y. This is the formula. Okay. Now we have been given the standard deviations. So essentially this is covariance of xy by sigma x. Root over variance of x is sigma x. Root over, because variance x is sigma x is square, variance y is sigma y square. So root over them it will be sigma x and sigma y. Alright.
Okay. Yeah.
Now covariance xy by sigma x sigma y. Covariance can be written as expectation of xy minus expectation of x into expectation of y by sigma x sigma y. Expectation of, so this one is expectation of xy. Expectation of x is mu x. This is mu y by sigma x sigma y.
Okay.
Now, so here we have been provided with mu x, mu y, sigma x, sigma y. Otherwise, we could also have derived it from here. We have the values and the probabilities corresponding. So expectation and variance we could have derived, and you can check it, you'll get the same thing as this one. Okay. So once we have these, so the only bottleneck here is expectation of xy. How will we get that? So expectation of xy is nothing but double summation xy probability x equal to x, or I, or I'll write it, y equal to y. in a bivariate sense. So then this would be how much? This would be, we'll just take product of xy and multiply it with the corresponding joint probability. Okay, so this would be, I'll just copy this thing again, it will be easier that way. All right, so here what will it be? It will be 1 into 1 into 0.25. So 1 into 1 into 0.25 plus 1 into 2 into 0.25 plus 1 into 3 into 0.25 plus, sorry, into 0. This probability is 0. Okay, plus 2
0
into 1 into 0
plus
plus
2
2 into 2 into 0.25 plus 3 into 2 into 0.25. This will be something
0.25 plus 0.5, 0.5 plus point, and this is 1, and this is 6 into 0.5, 1.5, 0.25, point half, 2, 3.25, okay.
we are getting this 3.25.
Yeah. Yes.
Okay, so this one is 3.25. So then substituting, what we'll get?
3.25 minus.
So rho xy will be expectation of xy minus expectation of x into expectation of y by sigma x sigma y. This one is 3.25 minus mu x mu y by sigma x sigma y. Mu x was 3 by 2, 2, half and root. So this is 3 by 2. Mu y was 2. Sigma x was half. Sigma y was root over 1 by 2. So this one will be 3.25 minus 3 by 2 into 2 by half into root over half. So this will be 0.25 by half root half. This will be 0.5 by root over half. How much is it coming to? Something 0.707, approximately 0.7. Okay. All right. So here again we are faced with a similar problem, but we've not been given the mu values. So first of all we'll find out the marginals. So x minus 1, this is 0.4, 0 is 0.2, 1 is again 0.4. This is the marginal of x. This is fx. If y is 0 0.4, 0 0.2, 0 0.4. It's adding up to 1. So mu x will be how much? Mu x will be minus 1 into 0 0.4 plus 0 into 0 0.2 plus 1 into 0 0.4, that is 0. Mu y will be what? Minus 1 into 0 0.4 plus 0 into 0 0.2 plus 1 into 0 0.4, that is also 0. Mu x, mu y's are 0. So variance of x, sigma x square equal to expectation of x square minus expectation of
x whole
whole
square.
square is essentially expectation of x square, because this part is 0.
0.
Okay, so this will be 1 square into 0 0.4 plus 0 square into 0 0.2 plus minus 1 square into 0 0.4. So it will be 0 0.8.
8.
And similarly, sigma y square will also be 0 0.8.
0.8.
Okay, so this thing we have. So here we have mu x equal to 0, mu y equal to 0, sigma x square equal to 0 0.8, sigma y square equal to 0 0.8. Now similarly we have to find out the correlation coefficient. How much is it coming to? So then rho xy is covariance of xy by root over variance of x, variance of y. So this will be expectation of xy minus expectation of x into expectation of y by sigma x, sigma y. So this
E of xy we did not find, no?
E of xy we have to find. This part is 0. Sigma x and sigma y root over 0 0.8, so it will be 0 0.8. So we will have expectation of xy by 0 0.8.
8.
Now we will find out expectation of xy. So expectation, where is it? Would be what? Minus 1 into minus 1, 1 into 0 0.20. This into 0, then again
1.
minus 1 into 0
0.
0.2.
So this will be 0.
This will be 0 for all. Then again minus 1 into 0 0.2 plus 1 into 0 0.2. So this is also 0.
Yes, 0 by, so 0.
So rho xy will be 0 by 0 0.8, which is also 0. So correlation is 0.
0 means they are not related.
No. There is no linear relationship. They are not related that way. Are they independent?
We cannot.
We cannot say. Why?
Because for being independent, E of the intersection should be
No.
0.
No. Whatever you told, that is mutually exclusive.
Okay.
Okay. Independent, when we say, yes, we can say from this table we can say. So the independence criteria, if you remember,
Probability,
fxy
yeah.
should be fx into fy for all xy pair.
Yeah,
If this
joint should be
holds,
product of marginals.
yes, if this holds, then for all xy, then we can say it is independent. But is it holding true? No.
No, no.
0.4 into 0.4, this is, it will be something 0.16.
What
But
6?
here we have
0.2.
0.20. So it is not independent.
Okay.
Okay. You can
Yeah.
check with others also. Same thing. Here we have 0.2, 0.4, but here it is reported 0. So it is not independent.
Okay.
Okay. Fine. Move on to the next one. Okay. Here we have, yes. Alright. So here what do we have? We have three jointly continuous random variables with a joint PDF of this. We have to find the joint PDF of x and y. So this is straightforward. PDF of x and y will be x, y, z over dz. Okay.
Yes.
So
Okay.
this will be 1 by 3 x plus 2y plus 3z from 0 to 1, that is the range of z, dz. So we would have half x, sorry, this would be 1/3 x plus 2y. So this will,
X Z plus 2 Y Z.
no, not z, dz.
Yeah, but we are integrating with respect to
Yes.
Z, no?
Hmm.
So
We
it will
shouldn't
be
write,
X Z plus 2 Y Z. The first two also.
we cannot write z, then z will come into the picture. This doesn't
Okay.
have z, no. So we have to write dz.
Yeah.
2y dz.
I'm telling final integration.
Oh, okay, final. Yes, yes. Final integration, it will come 1 by
X.
3 x plus 2y plus 3 into z, whatever this is. So this will be 3 into 0 to 1 z dz. So this will be dz in terms, this will remain x, this will also remain 2y. So we would have 1 by 3 x plus 2y plus 3 z square by 2. This will be 0 to 1. So ultimately we would have 1 by 3 x plus 2y plus 3 by 2. Okay. So and range will be 0 less than x less than 1, 0 less than y less than 1, 0 otherwise.
Okay.
Okay.
Yes.
Alright. So this was easy because there was no dependence. If we have comma over here, it
Hmm.
means they are not related. But if there are some less than equal to something maximum minimum, then we cannot do it in such straightforward manner. Then we have to look at regions where these are satisfied and work accordingly.
Okay.
Okay. So the last class or the last session, there I solved a few problems. The video is available online. You can go and check if you want to see how to uh, solve such problems when we have dependencies in the ranges.
Okay.
Okay. All right. So I'll move on to the next one. Okay, this one. Let x, y, and z be three independent random variables. We know these, so we have to find mu and sigma. This is also very easy. So expectation of x square y plus xyz equal to 13. Now the important thing is 3 are independent random variables. So if we have independence, then the product of expectations we can write as expectation, we can write it as,
Expectation of products is
yes,
equal to product of
yes,
expectations.
expectation of products equal to product of expectations. So this we can write as expectation of x square expectation of y as expectation of y expectation of, sorry, this
X,
x
Y, Z.
y expectation of z equal to 13. So expectation of x square is what? This is variance. Okay, we'll keep it here. Expectation of x square, expectation of y. So y and z they have given follows uniform 0 2. So expectation of y, here if you have any random variable p which follows uniform a comma b, expectation of p will be a plus b by 2, and variance of p is b minus a whole square by 12.
Okay.
Okay, so using these we are going to come here. So expectation of y will be how much? 0 plus 2
One.
by 2, that is 1. Variance of 1 will be 2 minus 0 whole square by 12, that is 1 by 6.
Yes.
Oh, no, 1 by 3. 4 by
Four.
12.
4 by, yeah.
1 by 3. So expectation of y is 1 plus expectation of x, we don't know. I mean, we know in terms of mu. Expectation of y will be 1. Expectation of z is also 1. So this is one equation. Expectation of x square plus expectation of x equal to 13. Let this be my equation 1. Similarly, here I have to find out the second. Okay, so here we have expectation of xy square plus zx square equals to 14. So we have expectation of x into expectation of y square plus expectation of z into expectation of x square equal to 14. So expectation of y square is, we can write as expectation of x variance of y plus expectation of y whole square.
Okay.
Okay, as expectation of z is 1, expectation of x square, we'll keep it like this for the time equal to 14. So we can write that expectation of x variance of y is 1 by 3
By three.
plus 1 plus expectation of x square equal to 14. So we have 4 by 3 expectation of x plus expectation of x square equal to 14. This is my equation 2. So now we have two equations. 4 by 3 expectation of x plus expectation of x square equal to 14, and from here we have expectation of x plus expectation of x square equal to 13. This was my equation 1. This was my equation 2. So 2 minus 1, we would have 1/3 expectation of x equal to 1, expectation of x equal to 3. So which implies mu equal to 3, because x followed normal mu sigma square. And we have to find out mu and sigma. So then if x follows 3, then expectation of x square equal to 13 minus expectation of x, that is 10, and variance of x sigma square equals to expectation of x square minus expectation of x whole square. 10 minus 9, that is 1. So sigma equal to plus 1.
Okay.
Okay, sigma can never be negative, so standard deviation is always positive. So
Okay.
from here the answer is mu is 3 and sigma is 1. Is it okay?
Yeah.
Alright. Just give me 1 second, my laptop is running out of charge. I'll plug it in and then
Okay, okay.
move on to the. Meanwhile, you can try to solve uh, this problem. All right. So this one, x order n is actually maximum of x1, x2, xn. So this is order statistic. Okay. So
Can you explain this order statistics concept once?
okay, I'll explain it. 1 second. Okay. So if we have let's say n random variables, okay,
Hmm.
then if we just arrange it in, let's say this is the smallest one, x7 is the largest one, okay. So
Hmm.
if we arrange x2 in an ascending order, and then this one becomes my minimum random variable and this one becomes my maximum random variable,
Hmm.
okay. So this is how so then this set essentially is my order statistic, okay. The definition is this: the function xk that takes on the values xk is possible assumed by this is the kth order statistic. That is, if we say the seventh order statistic, that means the seventh lowest value between these random variables, okay. And the joint pdf is given in this manner. This was discussed, and also the individual uh, kth order thing was discussed. 1 second. Marginal pdf, yes. So can you see?
Yeah.
All right. uh,
Marginal PDF is given by,
hmm.
this is not n factorial n minus r factorial into r minus 1 factorial.
Okay, so if we put r equal to n,
Hmm.
then that is the marginal of the maximum.
Okay.
All right. So f is the cdf and f is the pdf. So here also we'll do the same thing, we'll use this formula. So then if uh, so first we'll write it in this manner, or we can write it in this manner also. Fn x equal to probability that the maximum is less than or equal to x. So this thing Instead of using that, we can also write, if the maximum is less than x, it means all uh, the maximum is less than equal to x, it means that probability this thing all are less than equal to x. Or instead of writing here, I'll simplify it. This will be more. This means probability x1 less than equal to x, x2 less than equal to x, x3 less than equal to x, xn less than equal to x. Maximum is less than x. Whatever
Yeah.
we have, the max is less than x. So let this be 7, let this be 3, let this be 1. All x1, x2, x5, x7, everything will be less than equal to x.
Yeah.
Okay. Now x1 to xn, this is IID. So these probabilities are independent. So we can write it as probability x1 less than equal to x into probability x2 less than equal to x into probability xn less than equal to x, because they are independent. And we can write it as product of I equal to 1 to n probability xi less than equal to n. So
Xi.
so this one we can write. So here this is nothing but probability xi less than equal to x whole to the power n x1, because these are all identically distributed.
Okay.
Okay, because xi's are IID. So this is the CDF. Now x follows what? X follows exponential. So xi follows exponential theta. So fxi is theta e to the power minus theta x when x greater than equal to 0, 0 otherwise. Okay, and CDF of x will be how much? Fx will be 1 minus e to the power minus theta x if x is greater than equal to 0 and theta greater than 0. Okay, this is how the CDF of an exponential distribution looks like. So here we are going to substitute, and this will be 1 minus e to the power minus theta x whole to the power n. Okay, so this is the CDF. Now given the CDF, the PDF of xn is dd,
Derivative of CD.
yes, ddx of f of xn. So we had ddx of, what was it, 1 minus e to the power minus theta x whole to the power n.
But directly you have written PDF, no? Previous slide.
Previous slide I wrote CDF, this is CDF.
Somewhere. Where did we get only exponential function you have written somewhere?
Oh, these
Ah.
are IID variables. So this
So
is
f of xi
hmm,
here, theta into e raised to minus theta x.
hmm.
That is PDF only, no?
This is PDF. PDF of xi of one random variable, and this is CDF of xi.
Yeah.
Here the expression is whatever we have to the power n.
Okay.
Okay, so we'll write the CDF value expression that we got whole to the power n. This thing we are going to differentiate.
Okay.
Okay, so here we have n 1 minus e to the power minus theta x to the power n minus 1 into minus e to the power minus theta x into minus theta.
Okay.
Okay, so this will be something n theta e to the power minus theta x 1 minus e to the power minus theta x to the power n minus 1. Alright,
Okay.
this is the PDF, how it will look like. Now we have to do an expectation of x order n.
So integration again.
So then again we have to do
X theta x f dx.
So here again we have to do n theta x e to the power minus theta x 1 minus e to the power minus theta x n minus 1, and using the by parts thing we can actually this thing it follows a certain other kind of distribution which has not been taught yet. We haven't been taught about beta distributions, right?
Yes.
So this is a functional form of it can be transformed into a functional form of a beta distribution. So then we would obtain a closed form solution of this thing. Okay, finally it would the final thing would be 2n theta by 2 plus n. This we would obtain.
Okay.
So the main purpose of this thing was, even if we don't remember this formula, we can easily use this to get the PDF. But even if we don't remember, we can just derive it from the definitions. So CDF means that variable less than equal to x. If the maximum is less than x, then all will be less than x. Then we can write it as a product because they are independent. Then we can just do a to the power of n because they are identical, and then just differentiate from CDF. We would land up at the PDF, and then just put x, and we can go about in this manner. Similarly, if we want something like probability x equal to 1, if we want the distribution, this is the minimum. Okay, so then the thing is, same thing we would do, greater than equal to x, we would find out 1 minus CDF we would find out here. So the first minimum, if it is greater than something, then all will be greater than x. So this will again be probability of x1 greater than equal to x whole to the power n. So it will be 1 minus that CDF, individual CDF, whole to the power n. So then again if we do, so then the CDF of min will be 1 minus 1 minus CDF whole to the power n, CDF of individual random variables. Okay.
Yes.
So from here also then we can differentiate and get the distribution and mean, variance, whatever is required. Okay.
Yeah.
Alright. So now this one. So in simple linear regression, there is how many dependent variable and how many independent variables. So simple linear regression is something like this. Where this is my dependent variable, this is my independent variable, and this is my error term. So in case of a simple linear regression, we would have one dependent and one independent variable. In case of multiple linear regression, then we would have
Multiple
One
dependent,
dependent, multiple
independent.
independent. Okay. Okay. Then this one, linear regression analysis helps in knowing which of the following. So all.
It is linear regression analysis helps in doing which of the following:
Hmm.
causal effects in forecasting.
Forecasting trends, all of
Forecast.
the above.
Can you please illustrate by one example each one?
Okay, so let's say we have effects in forecasting something. So we have, let's say, X is my rainfall,
Hmm.
Y is yield of crops.
Okay.
Okay, so Y, it is expected if we plot rainfall along this axis and yield along this axis, we were expecting to see some plots like this, some increasing slope we want to see. Now let's say this rainfall is annual rainfall. Okay,
Hmm.
first year, let's say 1996, 97, and so on, so on, so on. Now we are fitting essentially a line. This is my regression line. Okay, this we are fitting over here. Now if we are given at some point, let's say 1950, sorry, to 2050, the amount of rainfall was so much, then what do? We just extrapolate, I mean, we put the value of X here and get a predicted value of the yield that is supposed to happen in 2050.
Okay.
Okay, so this is the
Forecasting.
forecasting trends part of the thing. Forecasting, effects in forecasting. So essentially, by fitting, we are, with the help of these plots, what we are getting is the beta value, that is the slope.
Hmm.
Before so from initially, what we have, if we have the raw data, we have this thing. So using the X and Y values, we are fitting a line such that the vertical distances of the points from the line is minimum.
Okay.
Okay, so this is my line, best fit line. It is fit in such a manner such that the distance, vertical distance of the points from the line is minimized. So using, so giving that regularization criteria, we would obtain beta hat and alpha hat, these values. So this beta hat is the effect, how much of an impact a 1 unit increase in X is making on Y. Okay,
Okay.
that is my beta hat. So if we have something like this, let's say very mathematically speaking, if we have Y equal to alpha plus beta X, okay, Y equal to alpha plus beta X, and Y curl equal to alpha plus beta X plus 1. So if we do 2 minus 1, we would have beta, or let's say X plus C. So we would have beta C equal to Y curl minus Y. Beta would be Y curl minus Y by C.
Hmm.
So we are increasing X to X plus C. So this essentially implies per unit increase or decrease in Y for per unit increase in X. So this thing also we are determining. So
Okay.
if I can give you another illustration, let's say, uh, let us talk up in terms of genetics. Okay, so we know that we have we have two chromosomes and we have alleles from two parents or something like that. So
Hmm.
here, if we have y as some variable, let's say my BMI, and this one, these are my, let's say, genotypes at genetic composition, something. So it can be coded as number of A's here. So it can be coded as 1, 2, 3, something like this. So here beta would mean that one copy of T is contributing to my BMI by how much.
Okay.
That calculates the genetic predisposition. So this is also some effect that we are forecasting. What, how much can 1 millimeter of rain influence the yield of a crop?
Okay.
How much can one single unit of power fluctuation make some errors or some things in production, something like this. So those will also come in forecasting, effect forecasting. And these are mere associations, but whether they are causal or not, that can also be found out by linear regression. Okay, some sort of causal analysis. So whether actually this is a association or a mere correlation, or we have some causal effects, it is actually causing something.
Example for causal analysis.
Causal analysis is not that straightforward with respect to linear regression analysis, but these models are inherently used in causal analysis. So one, it's not exactly causal analysis, but one thing I can say, let's say you have your x, you have a hypothesis x, these are associated, these are all associated, so this may be one root which is causing this thing. Okay, so if you can estimate, if you can uh, I mean tease out the effect of y from, or something like this, if we, this is essentially some sort of a mediation effect that I'm talking about. I'll come back to you with a more concrete example in the next class. But the thing is, we usually use linear regression analysis for some sort of causal analysis.
Okay.
Okay,
Yeah.
so huh. So I can't remember a very short and crisp causal thingy, but these linear models are used for causal analysis.
Okay.
Alright?
Yeah.
Okay. I'll get back to you on this one next week.
Yeah. Yeah.
Okay. So, this is the last question for today. Which of the following can be used to understand statistical relationship between dependent and independent variables in linear regression?
Correlation coefficient, then coefficient of determination. What is coefficient of determination?
Okay. So, let us consider a simple linear regression case. Okay.
Mm-hmm.
We would have y equal to alpha plus beta x plus epsilon. This is my model. So, from the data, we would have alpha hat and beta hat. These are estimates. Okay, plugging in this one and this one, we would have alpha hat plus beta hat x. This would be my, this y hat is the predicted value.
Okay.
Okay, so based on correlation coefficient is what? Correlation coefficient is the R thingy. Okay, and in case of a in case of any linear regression, coefficient of determination is determined by capital R square, which is variance of the predicted by the variance of observed. So our coefficient of determination, it lies between 0 and 1, and it shows how much of the variation in the dependent variable or the y we are be how much of that is being explained by our model, by
O-
these predicted thingies. So this is the formula wise thing. The interpretation is how much of the variation in y are we capturing with the help of any of our defined models. Okay, so for a single, for simple linear regression, this capital R square is same as the correlation square. Okay,
Okay.
but for multiple linear regression, it's not that straightforward.
So here only A could be the answer,
No, here
or
both,
both?
because this is also a performance matrix. I don't know whether you've used it or not, but R square, the higher the value of R square is, the greater we say the is the accuracy of our model. So the goal is to have something where R square is higher, because we want to reduce the this epsilon term is the error term. We want to reduce error as much as possible. Okay, so the total variance in y, it can be, so let's say total variance in y, it can be broken down into two parts. It can be explained variance or explained sum of squares plus some residual sum of squares which is unexplained. So total variance, I'll write it here, or total variance in y is can be broken down into explained part plus unexplained. Okay, this variance is actually my predicted. This one we would want to be as close to 0 as possible. Okay, only then we would have this coefficient of determination to be increasing to 1.
Okay.
Okay, so this can be used. So R square will give us the, I mean, strength of the linear relationship, and correlation coefficient, it can take, so correlation coefficient, it can take values from -1 to 1. So this can also give the strength and direction, whether we are positively associated or negatively associated. Suppose if we have a graph like this, then as x is increasing, y is decreasing. So here r is less than 0. But if we have a graph like this, here r will be positive. So this implies a positive correlation, this implies a negative correlation.
Okay.
Okay, but r square will always give you the strength. Higher, the closer it is to 1, the more is the strength of the linear relationship, and we can say that higher amount of the total, so if r square equal to 0.8, we can say that 80% of variance in y can be explained by the whatever model that we are using. By
Okay.
model I mean this thing.
Yeah.
We could have
Like,
different formulation, we could add quadratic terms, we could add some other variables in case of multiple linear regressions. We could do
yeah.
all sorts of things. Okay,
Okay.
all right. So I think I'm going to close today's session. If you have any doubts, you can ask me now.
Thank you. Uh,
Okay.
and appreciate your patience. Even if nobody joins, also you have to carry on the work.
Yeah, I have to do it.
That's what. So that is really great.
Thank you.
Yeah,
So I'll see you next week if you are available. Otherwise,
yeah,
I'll
yeah.
close the session
Okay,
today.
yeah.
Thank you so
I'll
much
do
for
it.
joining.
Yeah, yeah.
Thank you.
Thank you.